This chapter 15 is still about scatter plots, and you will learn how to deal with regression lines. When you see a straight line in a scatter plot, it is called a regression line. This line goes through the data points by producing the least vertical distance possible from the line to all the data points. You will not be drawing any regression line in this course. You will do it with a software and you will interpret them. When you have a strong linear correlation, as you see this one in the image, you can easily draw a line that goes through the points as close as possible to each one here. And it's a strong correlation. So you can safely predict the value of y, the value of the response variable, if you are given the value of the explanatory variable. But when you have a very weak correlation, like the one illustrated here, it is not easy to make any prediction. Data points are all over the place. They're not grouped into a straight line, so you cannot really predict the value of y, the response variable, here the blood pressure, if you are given the explanatory variable, here the body weight. A regression line in a scatter plot comes with a formula, and this formula is the following one here, y equals a plus bx. You probably know this formula because you have used it in high school, but you probably have used y equals mx plus b. It's the same thing, it's the same formula, but the order is inverted and the letters are not the same, but it means the same thing. There's a difference in math philosophy if you are doing math with a Cartesian plan or if you are doing math with statistics. So in statistics, we use the following one, y equals a plus bx. So this is the one you're going to use in this course because you're going to use it in university. So it's useful if you get used to it right now. So here, y is the unknown. It's the dependent variable. It's the response variable. You have to predict. X is the value of the explanatory variable. It's the value of this quantitative data. A is the y-intercept. It's the value of y when x equals 0. And B is the slope. It's the amount y changes when x increases by 1 unit. So B can be positive if there's a positive correlation, and it is negative in the case of a negative correlation. Let's try this formula here with this scatter plot you have seen already in the last chapter. The scatter plot illustrates the correlation in a couple between the age of the wife, here used as the response variable, and the age of the husband, here used as the explanatory variable. So here, the unknown, the one you want to predict, is the age of the wife if the husband is 60 years old. So I will use my formula here, y equals a plus bx. A is the y-intercept. In this case here, it is 0. And the slope is 0.95. So here I have to multiply 0.95 times 60 in my formula, y equals a plus bx. So here bx gives me 57 plus 0. So the wife here will be 57 years old if the husband is 60 years old. Now let's go back to our coefficient correlation R that you have seen in the last chapter. Remember, I told you that the value of R tells you about the direction of the correlation. It can be positive or negative, and it also tells you about the strength of the correlation. R being 0 means there is a weak correlation or inexistent. R being +1 or -1 means that there is a very, very strong positive or negative correlation. So in order to find what percentage of the variation in the response variable is explained by the variation in the explanatory variable? I will use a very simple formula, which is R squared. So if, for example, if R is 0.7, which is a positive correlation, medium, R squared will be 0.49. This is 49%. This would mean that 49% of the changes in the response variable, y, are influenced by changes in x, the explanatory variable. Let's see this example here, which shows a strong, positive, linear correlation between the weight gained and calories consumed. Here, R is 0.97, so R squared is 0.94. This is 94%. It means that 94% of the variation in weight gained is influenced by the variation in the calories consumed. Let's see now another example of a very weak correlation. In this scatter plot here, R is 0.2, so it's close to 0. R squared will be 0.04. This is 4%. It means that 4% of the variation in blood pressure is influenced by the variation of body weight. It also means that the rest, 96% of the variation in blood pressure, is influenced by other factors, lurking variables here, like genetics, age, diet, etc. Now let's talk about causation, because it is very tempting in social science when we have a very, very strong correlation between two variables, even a perfect correlation, to say that there is a causation, that the explanatory variable will cause the response variable to happen. But we cannot say that. A correlation, no matter how strong it is, remains a correlation. We can't say that A is causing B or X is causing Y. For example, if you find a correlation between smoking and lung cancer, the coefficient is 0.8. So the coefficient correlation squared will be 0.64. It does not mean that 64% of lung cancer are caused by smoking. No, it only means that 64% of the variation in cancer occurrence is influenced by the variation of smoking. So there is only causation here, not correlation. There's only correlation here, not causation. To say that there is a causation between two variables, we need to conduct a lab experiment, a lab behavioral experiment in social science. A causation will be illustrated by the drawing on the left here. X causes Y directly. This is what you can say if you do a lab experiment. Very often there are lurking variables in the background that would prevent you from saying that there is a causation between two variables. These lurking variables can cause a common response, so a third variable will influence your two correlated variables. Or sometimes there is confounding. Your two variables are correlated, but they are also correlated with a third variable. We'll see examples to illustrate that. A study came out recently by the American Heart Association, and this study showed a correlation between owning a dog and living longer. Clearly showed a correlation. But in the newspapers, those reporting that study were saying that owning a dog makes you live longer, which might not be true. There's no causation between owning a dog and living longer, but it's a correlation. Maybe there is common response here with a third variable. And this third variable may be having a high income. This study was made in the United States. So having a high income might make you more likely to own a dog because dogs are expensive, they're expensive to feed, huh? And in the United States, having a high income actually is correlated with a longer life because you can afford health insurance, you can afford having a better diet and a healthier lifestyle. So yes, there is a strong correlation between owning a dog and living longer, but maybe due to a common response to a third variable, that is having a high income. Or maybe there is confounding here. Maybe there is a correlation, yes, between owning a dog and living longer. But maybe there's also a correlation between owning a dog and exercising more. And exercising more will also make you live longer, being correlated with a longer life. So owning a dog is correlated with living longer, but is also correlated with other variables like exercising, for example, that are correlated with a longer life. So we call that situation confounding between variables. And again, the best way to infer causation between two variables in social science is by conducting experiments.